Okay. Es un honor muy grande estar aquí en el centenario de mi padre, que es justo este día, y el retrato me acuerdo mucho, está muy bien ese retrato. Voy a hablar un poco en castellano, y hay unas fotografías que salieron de la casa de mi hermana, Cristina, que vive aquí en Madrid, y también está mi hermana Carmen y mi mujer Joanne. Y vamos a ver unas fotos. Primero vamos a empezar con el padre de mi padre, que es el Blas Cabrera. Y una de las cosas que quería decir, que aquí se dice, vamos a ver si puedo, así. Aquí esto es la revista de Magnetics Letters, que es uno de los más importantes en el campo de magnetismo en los Estados Unidos. Y si se ve el año, esto es 2013, es este año, y cada año ponen en una de las revistas una de las figuras más grandes del magnetismo, y este año pues es el Blas Cabrera, y esta foto es de 1905, cuando era recién catedrático en competencia aquí en Madrid. Esto fue su mujer, María Sánchez Real, y aquí están en el año 1942 en México, sabían, en el exilio, y murió en 45. Y los niños, el mayor Blas, mi tío Blas, y mi tío Luis, y Nicolás Cabrera, aquí, okay, de los 6 años. Y si vamos, primero, el Blas Cabrera, muchas veces durante mi carrera me han preguntado quién es ese Blas Cabrera que está en la fotografía de 1930 de Solvay, sentado al lado de Bohr y al lado de Richardson y Einstein y Madame Curie, y siempre me da mucho orgullo decir que ese era mi abuelo. Y aquí vamos con mi padre. Estas fotos cuando tenía 20 años, ¿no? Era muy guapo, ¿no? Y aquí mi madre, el año que se casaron, en 1942, ¿no? Carmen Navarro Clavero. Y en los Estados Unidos, esto es el año 1965, mi padre, mi madre y los 3 de nosotros, ¿no? Aquí yo estoy a los 12, y mi hermana Cristina, que nació en París también. Yo nací en París y ella nació en París, y Carmen nació en los Estados Unidos y tenía 2 años, creo, aquí en 58. Y aquí los últimos 2, estos son de los años 80, muy cerca de esa conferencia, que la fotografía, ¿no?, que vimos de Sebastián. Y hay, en fin, las 2 caras. Aquí hay la cara muy amable con la familia, se ve que no tiene corbata, luego esto está en casa, ¿no? Y aquí, más serio, que nunca le vi furioso a mi padre, pero ponía una cara de serio cuando no le gustaba algo, que se veía bien que no le gustaba. Okay. Y en fin, y para mí es un honor muy grande estar aquí. Okay, ahora I'm going to talk in English for the scientific part, and what I want to do is describe the experiments that we're doing to attempt to identify what is the dark matter of the universe. I'm going to spend a short time with the cosmology, the reason why we believe there's dark matter. Most of the time I'm going to spend describing the detectors that we build to look for dark matter. And those detectors have much condensed matter physics in them, and so that's always been a very interesting connection for me, the use of condensed matter physics and technology to look for particle physics in the form of dark matter in the universe. So let's see. Y creo que se puede, you can see over there too. So direct detection, we build detectors to look for dark matter. The experiment that we're running is called the Cryogenic Dark Matter Search Experiment, CDMS, has led the field for most of the past decade, and is continuing with a super CDMS, Sudan. This is a mine in northern Minnesota in the United States. And we are working on a 3 times deeper mine in Canada called Snow Lab. And the cryogenic detectors used semiconductor crystals of germanium and silicon, and sensors made of superconducting circuits on the surface. And we'll describe how those work. There is competition, new competing technologies based on noble liquids, making significant advances with Xenon 100 now leading the field. And there are experiments, Dama Libra and Cogen and also CREST, which believe they may be seeing signals. Our experiment has largely ruled out WIMPs as being the origin of those signals, but it's possible something else is being seen. So I'll describe a bit of that, but let's go through the story of cosmology first. There are remarkable experiments. One type of experiment is the cosmic microwave background. And in this plot, along the x-axis, is the amount of mass in the universe, what fraction of the universe is mass, and therefore clumps and forms gravitational structures, versus in this axis it's the cosmological constant, what fraction of the energy of the universe is in a form that's causing expansion of the universe today. So it's called the dark energy. And the 3 types of experiments, this is the cosmic microwave background, which tell us that the sum of the 2 is very close to 100%. Here is the supernova, which allow us to independently measure the amount of mass and dark energy. And the third one is weak lensing. It's another way of measuring the total mass in clusters. And the interesting thing is they all give a common intersection at about 0.7, about 3/4 of the universe in the form of dark energy, which we know very little about, and about 1/3, 30% of the universe in the form of matter. And so the last satellite to look for dark matter in the form of the cosmic microwave background set very, very stringent, high precision limits of mass and cosmological constant. And the most important thing, if we look at the constituents of the universe, here is the 3/4 that's the dark energy. Here is the sector we're looking for, which is the dark matter. And we know now that the universe can only have 4% of its total energy in the form of atoms. Atoms is everything we know. So all of the stars, all of the galaxies that we see, the Earth, the Sun, us, all made of atoms. But that's only 4% of the total. And if we add up all of the stars and gas that we see in the sky, it's actually less than 0.5%. So there is missing atoms as well, but we know there can't be any more than 4%. And so the rest of this is in some other form. About 23% of the universe is in the form of dark matter. And everything in this sector, including neutrinos and the heavy elements, which are very, very tiny fractions, contributes to gravitational collapse, to clumping, to forming structure. Whereas everything in this sector does not form structure. It pushes things away and causes the universe to begin to accelerate. Now, the picture we have is quite remarkable. And so here is the computer simulation of how structure grows. So this is a cube of the universe that's expanding with the universe, so that you've taken out the expansion. And as time goes on, you can see that the structures become more and more dense. And they're filamentary structures, and the yellow are the crossing regions where you have the highest density. And that's where we believe that the galaxies form. Now when we do measurements in the skies, there was a huge advance by being able to measure the redshift, which allowed us to tell how far a galaxy was from us in addition to its position on the sky. And here is a slice through one of those surveys where you also begin to see filamentary structures, regions where there are voids and regions where you have high density. And so this cold dark matter in the form of gravitationally interacting particles, is very successful in constructing a universe that looks similar to the one that we're in. And so the picture is more and more certain that there's something out there making up the dark matter, and the question now is, what is it? What is it making up? And let me say one other final thing on the cosmology, that for me, this study of the so-called bullet cluster, there are about 1,000 galaxies in one cluster and about 200 galaxies in another, and they passed through each other about 500 million years ago. And as they passed through each other, the gas was stripped from the collection of galaxies, and you can see that in the X-rays. The red is the X-ray emission from these huge collections of galaxies. The white dots are the galaxies in an optical photograph, and the blue is where the mass is, which we measure by looking at the distortion of background galaxies as they move through that system. And so this is the most convincing demonstration that the dark matter doesn't get stripped the way the atoms do, and stays pretty much where the galaxies are. So a modification of gravity never allows you to have a non-local process like this. So this is the most convincing demonstration that whatever it is that makes up the dark matter is a fluid and particles, rather than a modification of our understanding of gravity on large scale. So what can it be? What can these particles be? We turn to particle physics, and there are many candidates. The ones that are the favorite right now are the so-called WIMP model. This is weakly interacting massive particles, and the structure that allows that particle to arise in the easiest fashion is supersymmetry, and the lightest supersymmetric particle is called the neutralino. So this blue region of the neutralino, being the type of WIMP that we're looking for, has dominated the searches to date. And the reason is that if such a particle exists that's about 100 times the mass of the proton and interacts weakly like a neutrino, that would give just the right amount of dark matter as what we see in the universe today. And so that's a rather tantalizing suggestion that this would be a good place to look. Another motivated place is Axion, and I'm not going to tell you about Axion searches, but there are several going on, and they're well motivated. It's always possible the dark matter is in some other form, like axinos or gravitinos, which would be very difficult to see. But you have to look one place at a time, and right now the WIMP hypothesis is the one that's favored. So that's where we're looking to see if we can identify dark matter in the form of WIMPs. Now, there's a troika. There are three major areas where dark matter could show up. And one of them is the LHC, tremendously successful operation over the last several years. And these points are different theories of neutralinos being the lightest supersymmetric particle. And as the LHC has continued to gather more data, it essentially it explores the region below the red line, and the red line moves out further. And you can see that these regions, so-called bulk and co-annihilation, have mostly been explored, and there's been no significant indication of a particle that meets these criteria, so that this region largely ruled out. The so-called Higgs funnel and focus point regions have not yet been explored fully and continue to be possible areas. Now, for our experiments where we look for detectors, with detectors that we put underground, these are the plots that you see. This is the mass of the lightest particle that makes up the dark matter, the lightest supersymmetric particle, about 100 times. So Here this is 10 times the mass of the proton, 100 times, 1,000 times the mass of the proton. And here is the cross-section. What's the probability of that particle interacting with a normal nucleon in one of the nuclei in our detector? And you can see these are 10 to the minus 44 centimeters squared, incredibly tiny probabilities. The experiments that we've done with CDMS have set a limit, shown by this black line, so all of the masses and cross-sections above that line are excluded at the 90% confidence level. And here you see the Xenon 100 most recent result, which has carved out a further down region, again, without seeing an indication of a signal. And the experiment we're currently running, which I'll tell you more about, in 2 years will achieve a line somewhere shown by this dotted line. And the next one that we're working on is 10 times larger and will reach somewhere around here. And notice that the Higgs funnel region, which is shown here, and the focus point region shown here are accessible to the direct searches and less accessible to LHC. Notice LHC has a limit from the energy that's being produced. It can't produce particles that are much heavier than about 200 GeV, something like that. So these regions we can explore before LHC. LHC in 2 years will go up another factor of 2, so this line will move up a little bit, factor of 2 or so. So there's enormous complementarity between LHC and the direct detection. And then there's a very interesting third leg to the investigation, which is called indirect detection. And this is looking out in space, for example, with gamma ray observatories to see whether or not there are annihilations of WIMP, anti-WIMP particles producing gamma rays. Also, you can look with the ice in South America, in Antarctica, to see whether or not there are energetic neutrinos coming from the sun. The sun would collect WIMPs. They would go to the center of the sun, annihilate, and an energetic neutrino would come out. Okay, if these particles exist, then very likely they will show up in at least 1 or 2 of these regions, and the combined information we get about it would give us a convincing story. So this is where we stand. Everything is limit so far, with a few hints that I'll tell you about. So here's where we stand today. The limits that I showed you from CDMS are here. These are the limits from the Xenon 100. These are now the theories that are left after the LHC data is put into them. And so they're just these smaller regions, mostly at higher mass. So the mass has been pushed up. There are experiments of DAMA and COGEN and CREST that suggest there may be signals at this low mass region. And so this is listed here. That Edelweiss is a similar technology to ours, and we've combined data. The purple line is the combined Edelweiss and CDMS. Xenon 100 is the black line. CREST is this region up in here and possibly there. And DAMA is the sodium iodide detector, which for more than a decade has claimed an annual modulation. And then these are the scientifically interesting theoretical regions of where supersymmetry and neutralinos. Theorists have come up with possible ways to understand a WIMP that's at about 10 times the mass of the proton, or even lighter. And in fact, with our experiments, and let me not go through the details for the motivations. Let me just say that with the possibility that there are WIMPs that have escaped detection at accelerators down below 10 times the mass of the proton, these are the limits that have been set so far about our existing experiment. Our new experiment will set this limit, and when operated in a somewhat different manner, can set a limit all the way down to here. So the crosses are not yet completed experiments, they're projections, and the solid lines are completed experiments, which mostly are not consistent with a signal if it's a WIMP. Maybe it's something else, but if it's a WIMP, they're not consistent. Maybe the other interesting thing to show here is I've been working, our group has been working on the search for dark matter for many years, starting about 1990. And this is the progression of sensitivity. So here's the centimeter square in cross-section with calendar year. And pretty much we've been along a trajectory of improving by a factor of 10 every 5 years. Okay? And we need to go another several factors of 10 to carve out the interesting region. And either we will find something or we will exclude that region from what's now the favorite model. Okay? All right, so now let me turn to the detectors. How do you build a detector to look for a weakly interacting particle? And the most important thing to realize is that weakly interacting particles don't leave a little bit of energy. They simply leave a significant amount of energy very rarely. So a reaction occurs very rarely. And it's relatively small amounts of energy because the particles are gravitationally bound, so they're moving slowly compared to relativistic velocities, right? Compared to the speed of light. So any detector you build will either see ionization. So if you strip electrons from atoms, that's ionization. And there are a number of different ways, systems to do that. We use semiconductors. The relaxation system often gives off photons, and that's called scintillation. Those are particularly easy to collect, so scintillation is a very important form. And then finally, all of the energy eventually ends up as heat, or phonons, lattice vibrations in the crystals. And a number of experiments have utilized 2 of these 3 possibilities in order to directly discriminate a recoiling nucleus in the crystal from a recoiling electron in the crystal. These WIMPs would only scatter off of nuclei and not off of electrons. So if you can remove the electron events from your data set, that's a huge benefit. About 10,000 to 1. You have 10,000 times as many electron recoils as nuclear recoils from backgrounds. So we do that in CDMS by measuring ionization and phonons simultaneously for each event. The xenon experiments, the noble liquid experiments, measure ionization and scintillation to do a similar discrimination. And there are even experiments like CREST, which measure phonons and scintillation to do discrimination. Okay, so each one, they're different. There are some experiments like the original CREST one and drift and coup, and also over here in X-mass deep and clean, which only measure one of the 3 at a time. And our own feeling is that it's very difficult to identify a signal with only one of the 3. And so we think that the combination of the 2 are the ones that are most important. Now let me give you then a sense of how do you think about these different phonons, ions, and photons from scintillation. So what percent of the energy went into that excitation? Eventually everything becomes heat, so 100% into phonons. Roughly 10% of the energy is in the gap energy of ionization, and roughly 1% of the energy in good scintillators comes out in photons. Okay, so it's 100%, 10%, and 1%. So each one smaller and smaller. The size of the quanta characteristic in the phonons we're interested in is a milli-electron volt, very tiny energy. In this community, that you understand that, and in high energy physics, they often mistake the little m for a capital M, and so you have to make sure. And the ions are 1 eV, so we're using semiconductors, so that's the characteristic energy. For noble liquids, actually, this is more like 10 eV. And then the photons are typically ultraviolet photons that are emitted in the noble liquid case, so the 10 eV. So then how many excitations are produced per keV of recoil energy? So we have 1 million phonons, about 300 ions, and about 10 photons. So if you're trying to measure 1 keV energy scale, you will necessarily have much higher resolution with the phonon signal, intermediate with ionization, and the poorest with the photon scintillation. Okay, and so here's the, and by the way, when you look at nuclear recoils, all the heat still ends up in phonons, so you still have 1 million. Less of it in ionization. There's less ionization for a nuclear recoil, 3 times lower, and about 10 times lower for scintillation. Okay, so again, for nuclear recoils, if you can see the phonons, good idea. And then this just goes on, carries through the noise of a typical amplifier for each of these three systems. You have very low noise for measuring photons, intermediate for ionization, and the phonons is similar. And so this is the full width half max that we achieve, about 1/10 of a keV for phonons, about 1 for ionization, and about 1 for scintillation. And then notice that the nuclear recoils have substantially less resolution for scintillation because there's even less of it. Okay, now here's an interesting overview of a whole field of particle detectors with time. So there was a tremendous breakthrough in the 1950s of sodium iodide, which is a scintillator. And here's the same spectrum shown with a sodium iodide detector. You can see bumps where there are going to be lines and so forth, but not very much resolution. Let me then move down here to the high purity germanium ionization detectors, which were invented in the 1970s, something like that. And notice that now we're measuring the electron hole production in the semiconductor, and we have substantially better resolution than sodium iodides. These became the detectors of choice for spectroscopy starting in the 1970s. You have to cool germanium to liquid nitrogen temperature because the gap is about 0.7 eV, so that the thermal excitations are too great at room temperature. And then a similar kind of advance has occurred with microcalorimeters, which are the ones that we're using in the dark matter search. And for these microcalorimeters, we've been able to get this kind of advance from high purity germanium to the microcalorimeters. Okay, so another order of magnitude and a half, about a factor of 20 or 30. And that allows a very impressive forensics of, for example, nuclear materials, where we can tell how much plutonium has been produced versus other materials, and that just opened up many different fields of research. Okay, so that's the direction. So what's in the detector physics? So we need to understand insulators with their Debye heat capacity. It goes as T cubed at low temperature. Conductors with Fermi liquid theory that go linearly in heat capacity at low temperature. Semiconductors with the electron holes with about 1 eV excitation. Superconductors, the excitations in superconductors are called quasiparticles, and they have about a milli-electron volt, so it's 1,000 times less energy than in a semiconductor. So if you can count quasiparticles, you will have factor of 30 better resolution than if you use electrons and holes for your energy. And magnetism, paramagnetism and diamagnetism give you mechanisms for reading out these systems. Okay, I won't go through what we're concentrating on the dark matter searches, but these detectors are used in many other fields as well, which are listed there. Okay, so let's just go through a simple picture of how do these detectors work. And basically you have an absorber where you're going to absorb the energy from whatever you're trying to measure, and then you want some kind of thermometer to tell you what happened in the crystal, how much temperature did it go up for the phonon signal. And then you want a sufficiently weak thermal link to the bath so that there is a time constant that allows you to accurately measure this step before it returns back to equilibrium. And this recovery time is just the heat capacity over the conductance through that weak link. And the change in temperature is given by the heat capacity, the energy divided by the heat capacity. Right? So that's a very simple system. So what do you use to measure the temperature? That's the key. And actually here we're showing pictorially the particle comes in, you get heating. And now what do you use? I'm going to show you 3 different systems and then show you that the results are actually rather similar for the very best ones. One is semiconductor thermistors. So this is using hopping conductivity, the change in resistance with temperature in a semiconductor that's doped just the right amount so that you can get a pretty sensitive thermometer. Change in the resistance gives you large change in resistance for a small change in temperature. And then those are read out with very simple circuits, and the absorber is connected to the thermistor, which then is read out with an amplifier. Now, the system we invented is called the Superconducting Transition Edge Sensor, TES, And this takes a superconducting line, and superconductor has the property it goes from zero resistance, as Doug Osheroff was telling us last week, up to the normal resistance over a very, very narrow temperature range. And so the idea is you bias the device in the middle of this very sensitive range, and a tiny change in temperature produces a large change in resistance. Okay? And here's the way we set it up. The trick in this was to realize that if you used negative feedback, you could automatically bias in the middle of this steep transition without having to temperature stabilize to remarkably high precision. And here's the way it's set up, that the TES, the superconducting element, sits in one arm of a parallel array. The other arm has a small resistor, shunt resistor in it. And then we measure the current flowing through this arm with a squid amplifier. That's a superconducting circuit that allows you to measure currents extremely accurately. And the shunt, what this is doing, most of the current from a current bias goes through the shunt, because this resistance is small compared to that over here. And that gives us a constant voltage across this arm. And the constant voltage has the property that the joule heating, the amount of heating of this device, goes as voltage squared divided by resistance. And that means we have negative feedback. When the resistance goes up, the joule heating goes down. And so if a little bit of heat goes in, then the resistance goes up, the joule heating goes down, and it restabilizes. So it's a self-stabilizing system where the temperature of the superconductor is maintained with joule heating. Okay, it's a very clever idea. It's like an operational amplifier that you use in electronics. And here we see that you have, as the resistance goes up, the joule heating goes down. And this is the way it looks then. You have a bias current from the constant voltage. An event occurs. You see a large drop in the current because the resistance went up, and then it comes back up. And the time it takes to come back up is actually artificially made faster by how steep this transition is. So this is the equation. The tau of recovery is the intrinsic thermal time constant, C over G, divided by roughly this alpha, which can be about a factor of 100, something like that. So we have very fast recoveries that allow us to have high count rates. Also, the integral that you have in this part here, the voltage times the change in current integrated over time, is exactly the energy absorbed by the TES. So again, all of these things make a very nice system for calibrating the detectors, and these have become the most sensitive detectors in a wide range of applications, including the dark matter search, for which they were invented, X-ray spectroscopy, gamma ray spectroscopy, and CMB. All are using these transition edge sensors as their primary sensors. Okay, a recent one, which is I think very interesting, is a dilute magnetic system, and using a squid magnetometer to read the change in magnetization of a dilute magnetic system with a DC squid. And this is the relationship of the change in magnetization with temperature as you approach. And these are the systems that are used, mostly the gold uridium, dilute concentration of uridium and gold is the favored system. Now, to give you an idea of how well these thermal measurement systems have worked, here is the K-alpha-1, K-alpha-2 X-ray lines from iron 55 near 6 keV. And for each of the three technologies, the transition edge sensor, the silicon thermistor, and the magnetic calorimeter, we see this remarkable resolution of the K-alpha-1, K-alpha-2. Notice, by the way, the dotted line is the theoretical width of the line just from the physics of the decay. And so these detectors are so good that the difference between the additional width from the finite resolution is just barely observable, right? And we see the very best ones are TES, but not by a lot. Within factors of 2, you've got systems of silicon thermistors and magnetic calorimeters. So it's very interesting that all of these thermal systems operating at low temperature have similar performance. Okay? And we'll say a little bit more about why that is here. So these are all equilibrium detectors, and much of the field in the past has used non-equilibrium detectors, and these are ones where Photons are counted with a scintillator, such as sodium iodide. The electron hole pairs in a semiconductor, and that's the high purity germanium detectors of the 1970s. And then the quasiparticles in a superconductor, tunnel junctions and kinetic inductance, or transition edge sensors, as I'll show you in a moment, can use these excitations that are quasiparticles in a superconductor. We do that in our dark matter search. I'll show you that in a moment. The very best detectors do have equilibrium, thermal equilibrium within the volume that's weakly coupled to the outside. And as I said before, the T cubed for insulators and the T for conductors are the key contributions to the heat capacity. See, I should go through this quickly. I find it very fascinating to look at the way in which an electron loses energy in silicon as a function of its energy. So very energetic electrons up here at a mega electron volt are in this beta block equation region. This is the so-called minimum ionization point, where beyond that in energy there's a logarithmic increase in the amount of energy lost per micron. And below that you get a large increase as you begin to get more into the condensed matter physics. So notice that this region where the energy loss per distance is rapidly decreasing is approaching the gap energy of the semiconducting silicon. And once you get below the gap, you can no longer, the electron can no longer produce an electron hole pair, and initially it can produce optical phonons, so that's this branch, and then the only thing you can produce after your lower energy than the optical phonon minimum energy is acoustic phonons, and that's this green branch. And finally, at the end of this green branch, there's not enough energy for the electron to be faster than the speed of sound in silicon, and no phonon can be produced at all. Okay, so that's the limit. And in this region here, as I say, if you apply an electric field, the electron will accelerate until it exceeds the speed of sound, then it'll shed phonons, and there'll be a drift velocity equilibrium condition. So that's the way in which we understand energy being absorbed by these systems. And maybe just saying a little more about the semiconductor diodes, where we collect the electron hole pairs. And the interesting thing is that the number of electron hole pairs is not equal to the energy divided by the gap. It's equal to the energy divided by a characteristic energy, which is typically about 3 times the gap. And what happens is about 1/3 of the energy ends up in excitations, which have the gap energy, the other 2/3 in phonons, which do not have enough energy to produce further excitations. So that's this epsilon, which is typically 3.7 for silicon. It's about 3.0 for germanium, as I show here. All right, then the other thing is, how many excitations do you produce? Well, the number you produce is equal to that energy per excitation times the square root of n. That you might expect that to be the RMS, the standard deviation of the distribution, but in fact we do better than that. And we write it as the same equation, square root of the gap times the energy times the Fano factor. And for silicon or germanium, this Fano factor is about 0.1. And I'll go through this here, but let's just go to the why is it that the square root of the number of excitations is not correct. And the reason is because correlations, if you follow a cascade, the green parts are the phonons that don't have enough energy to produce excitations. Those are lost, and you end up collecting the red parts, which are the excitations. And because the total energy is a constant amount, the correlations mean that you actually get a better resolution than you would just from the square root of n calculation that you have here. Okay, so this is the Fano factor. It's useful to go in and understand how that works in terms of the best resolution possible. Quasiparticles now, which are these excitations in a superconductor, they're broken Cooper pairs. We use tungsten, actually, which is not on this list. I should put it on the list. And it's down here in this region of 0.13 Kelvin TC, and the gap is very tiny, and the number of excitations is huge, associated with this small gap in a superconductor versus the large gap in a semiconductor. Okay, so now let me describe how we build detectors for different ranges of energy. So these are all transition edge sensors. They all use this negative feedback process of self-stabilizing the temperature in the middle of this very sharp transition. And for optical photon detection, so this is 1 to 10 eV, you can directly absorb the photon in the tungsten film. These tungsten films are typically 40 nanometers thick, and when the photon is absorbed, it changes the resistance and you get a signal, which I'll show you in just a moment. As you go to higher energies, say 6 keV, like the spectra that I was showing you, the tungsten is not sufficiently thin to stop very many of them, so you put bismuth, and bismuth is a semi-metal which has a very low heat capacity, electronic heat capacity, but it's a heavy element, therefore it has very good stopping power for X-rays being stopped in a relatively thin, a few micrometers thick bismuth film. So that's been very effective in the X-ray spectroscopy regime. Now, for dark matter, we need even bigger absorbers. We need to have a large crystal of germanium or silicon, that's this blue guy, and in order to collect the energy deposited in that crystal, we use a combined system of having aluminum films, and these are superconductors. The crystals operate at temperatures below 1/10 of a Kelvin, and the aluminum has a 1 Kelvin transition temperature, so this is superconducting. When an event occurs, energetic phonons enter the aluminum film and they break Cooper pairs. Now the thermal phonons, when there's no event, are below the gap of the aluminum so that they cannot break Cooper pairs. So you get no signal from the thermal phonons. Only the high energy phonons produced by an interaction of the crystal with a particle are absorbed. Those quasi-particle excitations then diffuse until they go into the tungsten, and that's how we get our signal. So we form quasi-particle excitations, then take their potential energy and put them back into heat in the tungsten film down here. Okay, and this plot, which I won't go through too much, it's a simple model of the different thermal elements. So this is the phonons in the silicon, and this is in the copper substrate that the heat sink that you're coupled to. These are the phonons in the tungsten, and these are the electrons in the tungsten. And for our system, the interesting thing is we're sufficiently low temperature that the coupling between the electron system in the tungsten and the phonon system in the tungsten is the weakest element. So that actually dominates the thermal model for recovery. And then you can go through and you can have specific predictions for what your resolution should be. For 10 keV amplitude, in other words, that you don't saturate for that energy, you can get down to about 1 eV, full width half max, so that's a remarkable almost factor of 10,000 in resolution. And for 1 eV in the optical, going through the same calculation, you get about 10 millielectron volts. So that's about 1 in 100, okay, about 100 times resolution. Now to give you, let's see, yes, so I have that. Let's see, I think I'll not go through exactly the way we measured the transition edge. When it's in the normal state, it's up here. This is voltage versus current through the transition edge. And here it is in the transition region. And we bias typically where this line occurs. And this is the resistance. So it's about 1/10 of the normal resistance. And this is the power. The power is about constant because the whole transition is within a very narrow temperature. So it takes the same power to maintain it in that transition with just a small change for the transition width. And then these are calibration pulses that show going from ones that are small, so these are self-similar, and then as you get to saturation they simply stay normal longer and then eventually come back. Again, if we take the integrals of each of these curves, it's a linear energy scale. So the integration of the curves is linear. And then one of my favorites, we did this demonstration back in 1998, and this is a single 20 micron square of tungsten and an optical photon in the green, 531 nanometer, that's the green laser pointer. Okay, those are the optical photons from that. This is one photon showing you the temperature rise in that tungsten piece, and the recovery. So you can measure each individual photon in the optical and get some energy resolution and timing. So we've used that for looking at pulsars, where you have rapid change in the properties of the emission faster than you can do with CCDs. So that's an interesting application. In terms of how well do the quasi-particles that are produced in aluminum films get into the tungsten TES, we've made these experiments where we have an aluminum film with a tungsten transition head sensor connected to both ends. And then we also have a surrounding a pair of parallel tungsten transition head sensors with aluminum fins connected to them. And what we do is we shine 2.6 keV X-rays on this system, and about 10% of these are absorbed in the aluminum film. And what happens then is we look at how much of the energy is absorbed in one TES versus the other, and you see this band of events right here. That corresponds to the ones that were absorbed in the aluminum. The ones up at this end were absorbed close to this edge of the tungsten, and the ones down at that end were absorbed close to the other edge of the tungsten. And notice that if there were no losses, if the quasi-particles were perfectly transferred to each of the TESs, this would be a 45-degree straight line. And so the bending of this line is a direct measure of the trapping length, and that trapping length is about 175 microns in these aluminum films. And we think that the quasi-particles are trapped by being trapped in local minima in the gap energy as they move across the film. And we're looking at ways to improve, to reduce the quasi-particle trapping so we can collect a higher fraction of the energy that's deposited in the aluminum film from phonons in our dark matter detectors. Okay, so that's an interesting type of experiment where we need to understand in detail everything about the phonon physics, the quasi-particles, and how the superconducting transition edge sensors work. And so that's very important. This is what our current detector looks like. So we call these, this is Z-dependent. We can measure the position of an event, ionization and phonon, and it's an interleave design. And let me show you what the patterns look like. So this is a picture of the surface, and here we've blown it up. These are the phonon sensors. Those shiny white regions are aluminum, and I'll show you in a moment the transition edge sensors, of which there are 1,000 in parallel. These are the charge lines which produce the electric field. So phonons are close to ground. The charge is at +2 volts on one side and -2 volts on the opposite side. And if we blow up the phonon sensor, you can see a tungsten 2 micron wide line going right down this region here, connected to each one of these aluminum fins. So the quasi-particles are produced in the aluminum, and they deposit their potential energy in the tungsten and heat up the tungsten, giving us a signal with an increased resistance. The huge breakthrough that we made in using the transition edge sensor was realizing that the negative feedback allowed us to easily instrument large crystals, because we had the problem that the tungsten properties were not the same all the way across the crystal. We might have one edge of the crystal a few millikelvin different from the other edge of the crystal in terms of the transition. The transition width was sharp for all of them, but you could pick no temperature in which you had sensitivity across the entire detector. That was a problem. And so the idea of this negative feedback allowed us then to bias them all, not quite at the same position, but very close to the same position, using the self-heating with Joule heating. So the crystal is much colder than the transition temperature, and each one is automatically self-biased right in the sensitive region. Huge advance. It means each one automatically worked instead of having to work very hard to get all of these properties to fit within a narrow band of just one, right, of these. And that's just the rest of the physics associated with that. And let me not cover, you can make the tungsten lines only so long before they phase separate into a normal and a superconducting. And we see that in the power curve, because instead of being flat, it starts being linear, because you basically have a superconducting region that's growing or shrinking and another normal region. So what do the signals look like from these detectors? So here's the phonon signal from a large 1.4 kilogram detector, in which when the event occurs, you see a large signal for the sensor that's close to the event and small signals for those that are further from the event. But after about 500 microseconds, all of the signals go to a common. And the reason for that is that the phonons have now gotten mixed in the crystal uniformly. They're not thermal yet, they're still athermal, breaking Cooper pairs in the aluminum, but they're uniformly distributed through the crystal. So it's a gray distribution. So an event that's close to one surface has this high peak on the surface it's close to, and an event that's in the middle of the crystal has about comparable peaks for the two that it's closest to on either side. Okay, so you can actually, from these multiple sensors, determine where the event occurred, whether it's a single point event, and then by comparing the ionization signal to the phonon signal, whether it was an electron recoil or a nuclear recoil. And when we have more and more sophisticated simulations, so here's the crystal, very interesting propagation of the electrons in germanium. They do not go along the electric field lines because of the anisotropies of the crystal. And the dots are phonons. And then here you see the simulated phonon signals reconstructed and the ionization signal, which occurs much faster. So for a nuclear recoil, the ionization signal is small, about 3 times smaller compared to the phonon total. And for electrons, you get a larger ionization signal. The problem we had in the past was that events occurring close to the surface had suppressed electron hole collection, because you had back diffusion preventing all of the electron holes from being collected. And the big breakthrough recently to improve the detectors further was this I that stands for interleaved. And we now have the phonons in charge on both surfaces of the crystal. So we have a ground, and here's, say this is +2. On the opposite side there'll be the ground of the phonons and -2. And when you do an electric field map, you see that roughly half of the electric field lines go across the crystal, and the other half go to the next nearest neighbor phonon sensor that's at ground. And this allows us to do what we call a symmetry cut. When an event occurs in the bulk, the electrons go one way and the holes the other, and both sides see a signal, one of opposite polarity to the other. And so that's what you see here. This is the charge collected on one side versus the charge collected on the other. All of these blue dots in the symmetry band correspond to events in the bulk. Now when an event occurs in this surface layer, then one sign goes to one of the electrodes, the other goes to the ground. And when we have here a cadmium surface electron source, you can see we can easily identify surface events because they're mostly in one, very little in the other. And so that was a huge benefit. It allows us to throw away all the events that are close to surfaces, which were producing leakage into our signal region in the past. And in this run at Sudan, these are the only data I'll show you for the run we're doing right now. We actually put in 2 electron sources. These are lead-210 sources, which is the main reason that we have these surface electrons. This is the beta decays from the radon chain. And these 2 sources produce here's the symmetry plot. So the ones that are in the bulk are in this region here. The green are neutron calibration. So we produce nuclear recoils of neutrons. And these are gammas up here in the gamma band. So 1 means that the charge to phonon ratio is that of electrons. And for nuclear recoils, it's about 3 times lower. All these red dots correspond to the events in the surface layer from this beta decay source. And the very nice thing is that we have sufficient rejection so that in the entire experiment, we do not expect to see any event leaking into the signal region from these surface electrons. So that gives us 2 orders of magnitude improvement over what we've had in the past. And it's also interesting in this plot that this band corresponds to the lead-206 that comes from the polonium decay. So after the lead-210 decays, there's several beta decays. You have a polonium-210, that alpha decays into a lead-206. So about half the time, the lead-206 up to 103 keV is incident on our detector. The other half the time you have an alpha that's up at 5 MeV. All right, and so this gives us very convincing demonstration that we understand our phonon calibration very well, since we get the 103 keV cutoff for the maximum energy of the lead 206. Okay, so I've gone on, so let me conclude. So the experiments now in the most exciting region of this neutralino space, exploring many of the models in minimal supergravity. And Xenon 100 now leads the field by about a factor of 3. And there are plans for going to Xenon 1 ton. Lux, dark side, deep and clean are progressing as well. And then our experiment, Super CDMS Sudan, is operating 9 kilograms of germanium. Will run for 2 years, which will get us roughly to the Xenon level. And then most importantly, we've been able to demonstrate with that surface electron rejection that a Snow Lab experiment with 200 kilograms will not be limited by the surface electron signal, so we know that we can get the sensitivity of a factor of 20. And I guess you can't read that too well, but we have a great horse race. That competition is very exciting, and I'm at the point in my career where I want to know what the dark matter is, and I care less about who discovers it. Okay, but it's very exciting time, and it is in many of the studies that the review panels have made, said this is one of the most exciting questions. The Higgs has been discovered now. What is the dark matter is among the most exciting questions you can ask. So let me stop there. Thank you. One question.
Very short question. At the previous thing you showed in a slide, a comparison between the detectors, the semiconductor detectors in Electron and Autónoma compared to silicon and germanium. So is there any way to overcome limitations of the semiconducting ones, not the silicon and germanium, the other one, the Electron, to overcome the limitations? Because I understand that in this way you will have a chance to work at the room temperature instead of at low temperature.
Right. So there are but see, all of them, the problem is you need a gap that's bigger than about 1 eV to work at room temperature, because otherwise the thermal excitations will produce some. If the silicon detectors are the very best at room temperature, and they produce about 120 eV full width half max, okay, for the characteristic. And if you want to do better than that, you do need to go down in temperature with at least thermal systems. And we don't know any other way around it. Commercially, the systems to make low temperatures are becoming easier and easier. The cryocoolers, etc., the sealed, you plug into the wall, and you can obtain temperatures even down below 1 Kelvin more and more easily. So that's an important enabler to these technologies. But if we could do it at room temperature, we would. To get down to these very high resolutions, you need to go to low temperature.
So could you use these extremely sensitive detectors to measure other things, not just single events, like background, CMB background?
Yes, exactly. So that's what I was saying, that right now almost all of the CMB polarimeters are using TES technology. So that's proven. The other very important question with respect to more and more of these detectors is multiplexing. So I showed you 1 pixel of the optical photon detector. CCDs have 8 megapixels, right, in your phone. So how do you make 8 million of these devices? And there are ideas for multiplexing where you have many fewer squid amplifiers than pixels, and you read them in series.
So what would be the sensitivity in microkelvin?
In temperature, in microkelvin. So that's a good question. I think we're in the nanokelvin region, roughly. Okay, is the temperature equivalent measurements.
So could you also measure polarization?
The polarization can be done, because what you do is you have antennas which couple in one direction and in the other direction, and you have one sensor in one polarity and one in the other. And then it's very important to have the rotation, so you calibrate to make sure the symmetry is understood, right? So you cross-calibrate. But it's been very pleasing. Dark matter may or may not exist, or we may or may not discover it. but the technology of this transition-head sensor is widely used and has had major impact, so that's very nice to see.
¿Cuestión? ¿Preguntas?
Más que una pregunta, quería hacer un comentario, pero quiero hacerlo en castellano. Porque, quería deciros que llevamos casi 5 años trabajando en el laboratorio para hacer los TESS, los famosos sensores de Transition Edge. Igual que nosotros, siguiendo un poco la línea que habéis desarrollado. Un proyecto interdisciplinar con gente de Barcelona, un grupo bastante grande trabajando en ese campo. Cuando ya tenemos los test funcionando, en ese momento es cuando ha caído el interés por la investigación en este país, hasta el punto en que ni siquiera teníamos dinero para invitarte a que nos explicaras cómo iba la continuación del tema, ¿no? Era fundamental para nosotros, para la pequeña comunidad española trabajando en este campo, tener tu experiencia y quería felicitarte por la maravillosa presentación que nos ha despertado todo el interés en aquellas cosas que nos faltaban. ¿Qué daño puede hacer un cambio de política científica como esta, puesto que ha cortado totalmente ese desarrollo que era para hacer un detector de rayos X en el espacio europeo, ¿no? Sí. Y bueno, de momento el grupo español está haciendo otras cosas porque somos totalmente...
La única cosa que digo es que también en los Estados Unidos se ha reducido bastante los programas para estos detectores del futuro.
Cuando ya sabemos hacerlos y queremos aplicarlos, es cuando precisamente desaparece el interés. Nada más.
¿Más preguntas? Bueno, Blas, hemos comprobado que en todos los sitios pues en Java. Te agradecemos escucharla tan bonita y tan brillante. Un aplauso.